Hi everyone, we're Team 1089 and our project is modeling predator detection in multi-species prey groups. The problem was to develop a mathematical model of how the animals in a group composed of different species interacts and observe their environment. So our main questions were, if a group is composed of different species, are they more likely to detect the presence of a predator? If so, what is the importance of the number of species? Is there a minimum number of species for there to be a non-trivial advantage? And is there an upper bound for the number of species in which additional types of animals have a smaller impact? To answer this, we researched and found data on how good each species is at detecting predators individually, what we call their P sub I value. For example, frogs have a very high detection probability of 0.94, while squirrels and deer are much lower, around 0.18 and 0.22. Birds and geese tend to be strong detectors, and we use those as a reference point in our model. These probabilities represent how likely at least one individual of a species is to notice a predator that's nearby. For our assumptions, we modeled a North American forest environment during the spring daytime, when animals are most active. We assumed all species could communicate alarm signals across the group, meaning K sub I equals 1, or perfect communication. The predator was kept at a constant detectable distance, and we assumed the same number of individuals per species to isolate the effect of diversity. In short, our model looks at how the mix of species affects detection, without adding complex behaviors or movement.
When developing our mathematical model, we decided to take a probabilistic approach where we calculated the probability that at least one individual in the species detects a predator. We used little pi to calculate big Pi, representing the detection probability of that species for a predator. We also used big N, little I, which was the number of individuals of that species I, as the exponent. Then we used big Pi alert to represent the probability of the individual's alert being spread. And to calculate this probability, we developed a parameter defined as communication efficiency that will be multiplied by the probability of at least one individual of that species detecting the predator.
We describe Ci, the communication efficiency for species I, mathematically as Ci equals to Ri of t equals to 1 minus e to the power negative Rit. It measures how effectively a species spreads an alarm through its group once a predator is detected. So if Ci is close to 1, that means the species alerts almost the entire group very quickly and vice versa. Here, Ri of t is the fraction of the group alerted by time t, Ri is the communication speed for the species, and t is the time window we're considering for predator detection. To reach the expression of Ci, we started with the first order differential equation. The initial condition for this expression is Ri of 0 equals to 0, as at time 0, no one is alerted. This expression here means the rate at which individuals are alerted depends on how many haven't yet received the signal, Ki minus Ri, multiplied by Ri. In this model, Ci equals to Ri of t. Ki represents the maximum communication reach of the species. Theoretically, if everyone in the group could be reached, we take Ki equals to 1. This is the assumption we will be using as well. And as described previously, the parameter Ri is the communication speed, which means louder calls, more visible postures, or more open habitats lead to higher Ri values. We begin by using our assumption of k equals to 1 and solving the expression by separating the variables and integrating it. We then apply the initial condition, Ri of 0 equals to 0, and we find that the constant equals to 0 as well. Now, substituting that back in and simplifying, we get the expression Ci equals to Ri of t equals to 1 minus e to the power negative Rit. We estimate actual Ri values. We started with birds because we had published data on their reaction times. We found that birds typically respond to alarm calls in about 0.1 seconds, so using the relation R equals to ln2 over t50, we got R for birds as 6.93 per second. We use R equals to ln2 over t50 because t50 represents the time it takes for half of the group to respond to an alarm. This connects observed behavioral reaction times directly to our communication model, where faster reaction produce larger Ri values. We then use the 6.93 per second as our baseline to calculate other species values using the formula Ri equals to Si times R-bird, where Si is a relative communication speed factor between 0 and 1, which we assumed based on sound, visibility, and habitat openness. The table shows the geese and beavers communicate relatively fast, while frogs and rabbits are slower. The list next to the table shows how we assume the SI values.
To calculate the probability that the group detects a predator, we use our previously developed piece of I-alert and the solution of our differential equation. The product operation would be used assuming that the probabilities across the species are independent of one another. This is the MATLAB code we use to simulate the effects of size and number of species within the group of animals that we chose to calculate the probability of the group detecting a predator. As previously shown, we chose 8 species with the respective parameters, and so we listed these parameters in MATLAB as matrices. We ran appropriate loops using our mathematical models across these matrices to calculate the probabilities that we were interested in. This is the first plot we did, and this is the communication coefficient, also representing C sub I, our communication efficiency parameter, across the different animals that we chose for our group. And this is simulated over time. This plot represents differences in how effective these different species are in communicating their signal over time. These differences will influence the probability of detecting the predator as a group, as you'll see in the next slide. So in this plot, we graphed the final group detection probability over the number of species. You could see that increasing the number of individuals in each species, which is represented by the different colored lines, increases the probability of the group detecting a predator. This is also the same when you're increasing the number of species. We also see that the steeper slopes represent the greater contribution to increasing probability of groups predator detection of adding that specific species. As the number of individuals per species increases, the lesser the effect of increasing the number of species on detecting a predator as a group. We noticed that 2 species is the minimum number of species for there to be a non-trivial advantage, as seen by the huge jump from 1 to 2 species. The upper bound of number of species for smallest impact is dependent on the size of the group, but in this particular group, we stated that it was around 4 to 5 species where we know a very small impact on increasing the final group detection probability. This slide summarizes the interpretation of the previous graph I just talked about.
Our model does have a few limitations. First, we kept the predator's distance and detection range fixed, so it doesn't change throughout the simulation. We also assumed perfect communication between all species, meaning every animal can hear or see the alarm right away. Each species was modeled with the same number of individuals, so we didn't include any group hierarchy or spacing effects. We also didn't include any noise, false alarms, or adaptation over time. Finally, we didn't model environmental complexity like sound distortion, vegetation cover, or obstacles that could affect detection. Our results show that mixing species with different detection and communication abilities significantly increases overall group vigilance. Species that detect faster or communicate more efficiently, like birds and geese, dominate the early warning. Adding more species helps at first, but after about 4 species, the improvement becomes smaller, showing diminishing returns. We also found that larger groups amplify detection overall, but the benefit of adding new species decreases as group size increases. These findings align well with what's seen in nature. Cooperation and diversity make prey groups safer. In future work, we'd like to add spatial modeling, including detection radius, distance between animals, and imperfect communication. We also want to explore predator strategies like stealth or speed, and eventually compare our predictions with real field data from mixed flocks or herds. All of our data and theoretical framework were based on the sources listed here. Thank you for watching.